Oh my goodness. Hello, hello. All right, I have to admit, hi. Hello, Maisha. And hello, Eric. Now, this is very tricky. I'm in a spot here, folks. Hello, and of course, hello, everyone. I'm waiting for the further hellos. Where are you guys? Um, I'm going to admit right now, and I usually don't go down this road. This is a dangerous invitation, but I'm totally saying hello to Maisha, but I'm admitting that I'm in a bit of a spot because I know that John Ford was in the waiting room for a while. I'm just saying. And again, it's gone the other way at other times. There's been other moves in other directions at other times, but I just feel compelled to note that fact. And meanwhile, John Ford's not saying anything right now. I don't know what that means, but anyway, hello, 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 hello. Okay, I'm just being silly. Yeah, okay, fair. Oh, all right. At least I got acknowledgement from both. I mean, what kind of idiot am I to be? I mean, it could have been the one class where there was no madness, and I'm just kicking it up. I'm just asking for trouble. It's all on me. But yes, okay. Hello, hello. Oh, and more people are coming. Okay, okay. So we're gonna start. Whoa. Whoa. Okay, that is a little creepy, I have to say, but okay. Oh, okay. Oh my God. Hello, Lizzie. See, now that's class. Wait, she class act, right? She just says hello. She shows her video. She's just saying, she's just, you know what I'm saying? All right. Anyway, hello. Yes. Hello, Lizzie. And hello. Oh, that's funny. Okay. But also hello, May. Hello, Jayla. Hello, Newell. Hello, Elizabeth. If I didn't say, I mean, the other, Elizabeth with an S. Oh, no, fair enough. Okay. Okay. Hi and hello. Good to see you. Okay. And again, hi. Okay. And again, I hope it's clear. I do want to make it clear for people that I'm still getting to know a little bit better. I hope it's clear when I do this hello thing, it's partly to be silly and human. It's not, it's not, oh my God, it's not attendance. It's an acknowledgement of people who are here. I'm not looking at who's not here, just for whatever that. And that now lab is different. Like lab, you have to do what you have to do. But anyway, okay, okay. Let's get rolling. Just trying to remember where we. Sorry, I'm momentarily forgetting where. Well, okay, we're just going to get rolling back to the material. Again, I owe you guys a lot. You don't owe me anything unless you do. But, oh, hey, May, that's cool. And hey, that's cool. Okay, yes, hey, May. Good May. Okay. Obviously, I owe you. It's still a little bit chaotic. I owe you game turns. I owe you homework one. I apologize. It is acknowledged. I mean, it is understood, and they will come back. And hopefully, I'll do some more catching up this weekend. But again, you don't have any new homework. We're all still living in homework one here. So let's go back to homework one right now. Oh, excuse me. Didn't mean to do that. Okay, we are at boom homework one. All right. We are at today. As usual, what's on the board here is sort of the goal of where we're going to get to today. Well, no, the top equation is what I think we have more or less established in previous classes. But I believe, although you should correct me if I'm wrong, but I'm actually sorry, I'm having a brain. Let me make this clear. The bottom two equations on the sheet right now are what I want to get to today. I don't expect necessarily that you've seen the bottom two equations, or at least not the way they're written right there. They're not old news. They will be new news today. That's what we're going to get to, the bottom two equations. But let me ask you, actually, I'm having a momentary lapse of confidence. Have we mentioned, oh, don't hit, wait. 1 second, hold on. Okay, okay. Sorry, I'm getting a direct chat. I'm acknowledging, but I'm gonna move on. That's funny. Wait, actually, I didn't even know. Sorry. Yeah, I don't know how I function. Okay, I'm reading the direct chat. I'm getting myself distracted, but I have to ask. This is a serious question about physics to all of you because I'm suddenly having a lack of confidence here. Have I mentioned kinetic energy in this class, like this semester? Have I said anything to the effect that I did? Okay, and I said that work is the transfer of, okay, great. Phew, for a second. So we established that work is the transfer of kinetic energy or change in kinetic energy. We said that. Okay. Okay, thank you. So I'm going to pick up from, so one way of putting that is the top equation on the sheet then. I mean, there's different ways of saying it, but hopefully, the left side of the equation at the top of the sheet here, the left side, that integral means work. And then the right side says delta KE, delta meaning change or difference in change in kinetic energy. And when we did the algebra, assuming we did the algebra, like the algebra seems to suggest if I do work on a system, I change its kinetic energy from one value to another. Kinetic energy just being the name. Oh, yes, I did say this. Kinetic energy being the name that we from here on in give to the quantity 1/2 mv squared, right? And I want to say that again, like when we say from here on in, or when you've ever said in another class that kinetic energy is 1/2 mv squared, I want to make it clear that's not a discovery. It's not. It is it is almost a definition, or it is a decision, I should say. 1/2 mv squared is that particular combination of measurements or of descriptions. It is that particular strange combination of measurement descriptions of a system that we would otherwise never care about. Like, I certainly did not wake up and on any morning and think, it would make a lot of sense to square the speed of some system and then multiply by its mass and then divide by 2. Like, oh, I logically see how that would be an important thing to do. Like, no physicist ever said that. We're not saying that it should be the case that we would ever care about 1/2 mv squared. We're just saying that actually, once we define this concept called work and we do a little bit of algebra, it turns out that when you do work on something, what you change is the 1/2 mv squared of that something. Like, I'm being serious right now. Like, that's just that sort of algebraic discovery that and that you change it not just sort of loosely or qualitatively, but that quantitatively, if I do 3 joules of positive work on some mass, then that mass's 1/2 mv squared will go up by exactly the amount, 3 joules, like, and the units work and everything. So okay, so that's what so therefore we decide to, I'm just reviewing now for a moment, or just trying to bring myself up to speed. So therefore we start tracking this quantity 1/2 mv squared, and we give it a name, and the name is kinetic energy. And so from here on in, we say the following. So I'm going to add a page here. So again, just to put it in perspective now, sorry. So if when I do work on a system, I find that the system 1/2 mv squared goes up by exactly the amount of work I did, or if I do negative work on a system, then the system's 1/2 mv squared goes down by exactly the amount of work I did. We find further, if we look at it further and we think about Newton's third law and think about how all forces are in fact mutual or symmetric interactions. That is, I can't push you without you pushing me back. And if I push you to the north, you necessarily push me to the south, or whatever. So if I do positive work on you and I give you kinetic energy, it's also the case necessarily by Newton's third law that you've done negative work on me. and I've lost kinetic energy. So the really, I think, helpful, best way to view this relationship between work and energy, like the thing that it says right here at the top of the page, it says it mathematically. It says work done equals change in kinetic energy. But I want to say that in English now in a slightly, I think, more helpful way, just in case I didn't say it before. Sorry. I want to say then, that is a subtle distinction, but it really helps me. Like, instead of just thinking of work as a change in energy, because that sounds confusing, then I don't know like whose energy is being changed and what I want to say from here on in. Again, forgive me, maybe I did already say this Monday, but I just want to say as clearly as I can in English. From here on in, work is the transfer of energy. Energy is the ability to do work. Now, if you are hearing me, if you think that sounds a little bit like a circle, if you think that sounds a little bit like, yeah, like circular reasoning, then you are definitely hearing me, and that's good. Like, it does sound a little bit like a circle. It is a circle. But if you're really letting it sink in, you'll realize that it's a circle in the same way that money is. And again, forgive me if I already said this Monday, but like, work is the transaction, energy is the commodity. Energy is like money, work is like spending money. Like, I want money. Why do I want money? Why do I want to be rich? I want money because the more money I have, the greater ability I have to spend money. The more money I have, the greater ability I have to get rid of the money. That almost sounds weird, but we all know that it's like true. Why is it true? Why does that work? Because when I spend money, when I get rid of it, the whole reality is that I get something in return for that money that I think is of a different form, but of equal value, right? When I spend, I don't just like lose money randomly. I get some, and that's the same way that work and energy work. Energy is the ability to interact with other objects and change their position or some other aspect of them. Energy is the ability to interact with other objects and change their position. When you interact with other objects or other systems and change their position, you give up some of that energy. And whatever energy you give up, they get. Work is the literal transfer of energy. Okay, just to make that as clear. So like, that's like the summary of what we were saying Monday. So now I'm going to go further with that. And why I'm developing this is I want to get an answer to question 5. I believe, now correct me if I'm wrong also, I believe that in this class, one way or another, we've gotten an answer to question 4 in the homework, in homework 1. Stop me if I'm wrong, but I believe we've done question 4. And now I'd like to move. Yes, thank you, Lizzie. All right, awesome. See, video is so helpful. See how she just did. And thank you, Elizabeth. I totally appreciate it. I totally see that. But see how her face said yes. Okay, anyway. All right, so we did question 4. So now I'm going to go on to question 5. And I'm going to sort of do what I I'm going to go on to question 5. So, okay, so here comes question 5. Now, what you see on the page is my work. Like, I'm going to ask you to indulge me just like last time so that we can feel like we're making concrete progress. I've written out my solution to question 5 right here. And I'm telling you right now, the answer that's sort of written on the side circle, the answer is approximately 0.095 meters. I'm going to back up and try to explain the work I did here for sure. I mean, that's like, in fact, the whole class today is going to be me trying to explain some of the implications of this work. Your work might look different. it is definitely possible that you did this a slightly different way, or maybe what seems like a drastically different way. And if you got the right answer, in this case, I'm going to say, even if you did it a different way, but you got the right answer, then I don't think it was a coincidence. I think your way is probably right. We'll find out. And I'm not saying you have to do it my way. I am saying that ultimately I want you to understand my way. So when I spend the rest of the class talking about it, I do want you to take notes and get it. Even if you did it a way that works, great. But I want us all to see this. But also just since I tend to talk a lot and all of that, I first want us all to sort of get this down and just have this at our disposal. And I want everybody to be able to know whether they got the right answer or not. So I'm going to start talking this through a little bit. But so here's question 5 from homework 1, and it says, for diagram and facts, please see the previous. So that's like step 1. Step 2, what's the question? So now I'm going to remind you. So again, I'm just talking this through while you hopefully copy it down or whatever. The question of question 5 was the question in the sheet was, find the position or compute or calculate or determine the position at which the instantaneous speed of the mass is 3 meters per second, right? Like that's the question. Like when the speed is 3, find X. And I believe the answer is 0.095 meters. Actually, and I'm going to explain why. Again, I'm going to explain why. But by the way, before I go any further, something just hit me. And in fact, it's actually funny, the other class didn't bring this up. Technically, there's 2 answers to this. I mean, I believe the question, again, I think the question asks, find the position when the instantaneous speed is 3. So actually, technically, both physically and mathematically, there really are 2 answers to this question: positive 0.095 meters and negative 0.095 meters. Because if I'm remembering the question correctly, if the question actually said find the position when the speed is 3, then the truth is that it could be on either side of equilibrium. It could be when the mass is going to the left or when the mass is going to the right. And the math supports that. So actually, if you got 0.095 or negative 0.095, then you really know what's up. But okay, what I did was, okay, 1/2 kx squared plus 1/2 mv. I said 1/2 kx squared plus 1/2 mv squared at the place where v equals 3. In other words, at the x that I'm looking for, equals 1/2 kx squared plus 1/2 mv squared at some other place, a place that I know something about. I'm comparing 2 positions here. I'm comparing the position x that I'm looking for to the position that I know something about. And what do I mean something about? I mean, I'm comparing it to a position where I know the speed. I happen to have picked the position where I know the speed to be 0. That is, so the position that I'm thinking about on the right-hand side of this equation, the position that I'm thinking about is x equals 0.15 meters. I eventually do plug that in, you'll see it. In other words, x naught. Now, again, I think it's my job today to explain exactly why I set the problem up this way and where I got that from, but that's what I'm trying to say in the first line. And then from then on, it's algebra. But that first line, okay, the first line, wait, something's in the chat. I'm sorry, hold on, let me just see the chat. Okay, that first line that I did, 1/2 kx squared plus 1/2 mv squared equals 1/2 kx squared plus 1/2 mv squared. Frankly, that's a line that many of you might have, or you might have something like it. There's various different ways you might have come to that line. You might have even have gotten it from the web and not be quite sure why or something. Again, my job in the next few pages is going to be to explain that first line, to really show you what the GDP, what the general definition and principle is from which that line comes. But the first thing I want to say is notice that my first line is not simply 1/2 kx squared equals 1/2 mv squared. Like, put another way, when we answered question 4, after we did a bunch of discussion and established what work and energy mean, we ended up writing 1/2 kx squared equals 1/2 mv squared. Now, this question is very, very similar. It's also ultimately about energy and work, but I'm not just starting with the simple statement 1f kx squared equals 1f mv squared. If I did for this question, it would be a mistake. This question is almost designed to very early on in the semester caution you that you never want to memorize or just assume something like 1f kx squared equals 1f mv squared. Like that is not a general definition or principle. Okay, what is the general definition or principle? Like what's going on here? Okay, well, one thing to notice. Question 5 names a speed. It asks you to find a position. That is basically just the reverse of what happened in question 4. In question 4, I named a position. I asked you to find a speed. What I'm urging you to see is that sounds like a very simple question. I mean, it is simple, but it's not easy. And it is different from the kinds of questions we were asking in Physics 203. In Physics 203, we tended to ask questions like, I name the time, you tell me the speed, or you tell me the acceleration, or you tell me the position or something. It tended to be that like time was the independent variable in Physics 203. Here, we're looking at situations where things depend on space, not time, where things depend on position, not time. And particularly here, like acceleration and force depend on position. And I'm asking in question 4, I'm asking, given some position, what's the instantaneous speed? Then in question 5, I'm just reversing that, but it's the same correspondence. I'm saying, given some speed, what's the position? We're embracing a speed position correspondence here. And what I want to say is the same thing I said in question 4. Whenever that comes up, if ever someone says, I'm naming if anybody ever says, I want a correspondence between point in space and instantaneous speed, then that's screaming for work and energy to be the way that we solve the problem. Question 4 demanded work and energy. Question 5 demands work and energy as well. So this is a work and energy problem too. However, my opening statement's involving work and energy is a little bit more complicated than my other opening statement. Somehow the details of this work and energy problem are a little bit more involved, largely because in question 4, I named a spot and asked for the speed. And the spot that I named in question 4 was x equals 0. I said at x equals 0, what's the speed? And the 0 there actually made the question a little bit easier. Here, I'm saying, I'm not only flipping it and saying, I name the speed, you tell me the spot, but the speed I'm naming is 3. And the spot you're going to find is not 0. Like there's more numbers involved here. Sounds stupid, but that's just the reality. There's more numbers and less terms being crossed out. So I want to take a step back. Oh, sorry. A good question, John. Wait, let me see. Wait. Oh, sorry. Yes. Excellently observed, John. Yes, my number is, you're absolutely right. There is an error. Sorry. Yes, I ran out. That is all supposed to be over. The good news, he's absolutely right. Hold on a second. Let me fix that. That's all supposed to be over. That's very good. All that's supposed to be over K. Yes. And the good news is, I'm just trying to make, hold on a second. No, he's absolutely right. Let me just fix that. But it doesn't change the number. Luckily, the number, the final answer is still the final answer because I just know that. But he's right. Let me just, how can I? Okay, no, yeah, John's absolutely right that I had a missing K there. It's all supposed to be over K, but if you plug it, but luckily I had already done the numbers and just like didn't do them out on paper. So the number, I mean, you can check, the number still works out, but yes, he's right. That is a good observation. Okay. Now I've lost my train of thought. What I was saying. I'm going to flip the page. This is the work, but I'm trying to everything the rest for the rest of this class, everything I'm going to say is meant to teach you the concepts behind this. Like I'm going to unpack this and try to teach you concepts, some of which some of you have heard before, some of which you haven't. But everything I say for the rest, basically what's written here is basically sufficient for you to write for your homework. Basically, like maybe missing a lot. Everything I'm saying now is like me teaching. Okay. And it's all teaching through the lens of this example. Again, as I've tried to explain or warn you, homework 1 is sort of like a bunch of questions that are meant to force us to unpack all these concepts that we need for the rest of the semester. So each question is kind of like an excuse just to get us into concepts. So the rest of what I'm going to say, please take notes and stuff, but I'm not expecting the rest of what I say. I'm not saying you have to write it all in your homework. I'm just saying I want to know it. So first of all, I'm saying, where did that statement, this statement, 1f(kx squared plus 1f(mv squared equals 1f(kx squared plus 1f(kx squared), like, where did I even get that in the first place? Well, if I move back a step and do GDP, the general definition principle, the definition or principle that I'm doing here is this: total amount of mechanical energy at position 1 must be equal to total amount of mechanical energy at position 2. Okay, like, so from here on in the class or whatever, I'm going to use capital E to stand for total mechanical energy. And then like capital E sub X or sub X sub N means the total mechanical energy at some position. From here on in, we care about energy at a total amount of energy at certain positions, because remember, this whole thing is coming up because we now have forces and accelerations and speeds and so forth that depend on position. So we're looking at situations where quantities vary as a function of position. So I'm going to define from now on capital E to mean total mechanical energy at some particular position, xn. All right. And I'm asserting right now that for certain kind of systems, systems that we're going to call conservative, I'm asserting that the total amount of energy at any one spot is conserved from that spot to another. That no matter which spot you look at, no matter which position you look at, as long as it's a certain kind of system, the energy won't change from one position to another, the total amount of energy. Okay, so I'm saying that this is going to be true for what we're going to call a conservative system. So the questions that remain, though, the things that I want to show you are, number one, what do I mean by a conservative system? Also, what exactly do I mean by total mechanical energy? I haven't said yet. That's what I want to say. All right. So again, so it says on the top, like, all this is expanded and for teaching purposes. Like, I'm not expecting you to write all this in your homework, but I do want to point out, okay, here's an observation. This says observation. I want you to, so I'm going to take a step back and like, I want us to notice something. Remember, bearing in the back of our mind that work is defined to be the integral of force with respect to displacement. Work is defined to be how much force you exert throughout some interval of space, right? That's what work is. Now, I want you to notice some and only some, that says some and only some forces will do or perform a net amount of zero work throughout around what English speakers would call a round trip, or what a physicist would call a closed path. Let me explain what I mean. Like some forces, if they push you out and then push you back in, or if they pull you out and then pull you back in, they'll do a lot of work for that entire operation. Other forces, if they push you out and then pull you back in, will end up literally and necessarily and predictably doing no work for that entire operation. That's a major distinction. the forces that end up doing nothing for an entire round trip are called conservative, because work is the transfer of energy. When I do work on a system, I give it energy. When I do positive work on a system, I give it energy. When I do negative work on a system, I take away energy. If we observe that in certain situations, certain forces will not do any work at all over some interval, then they don't give or take away any energy. They conserve the amount of energy, and we call them conservative. Now, let me break down what I mean. Let me give you a specific example. Take on the one hand, friction. If I look, imagine this stylus, imagine this stylus is being pushed along my hand toward you, like it's being pushed along the rough surface of my hand toward you. It's being pushed by my hand or whatever, and that's fine. But let's focus on the work being done by friction from this surface on the stylus as the stylus goes toward you. While the stylus is displacing toward you, let's call toward you the positive direction. While the stylus is being displaced toward you, the force of friction, of course, is pushing the other way. It's opposing the motion, as friction always does. So the stylus is being displaced in the positive direction, while friction is acting in the negative direction. A negative times a positive is a negative. So while the stylus is going toward you, friction is doing negative work on it. Right? I mean, that's not meant to be a surprise. I'm just like saying that. I'm just saying that. And let's even just put random numbers to it, just for an example. Let's say that the force of friction is 13 newtons, negative 13 newtons. And let's say the displacement is positive 2 meters. I'm just making up numbers. Then the total amount of work that friction does while the stylus is going out towards you would be negative 26 joules. Again, I'm just making up numbers, but just bear. Now, so the pen is being, and meanwhile, by the way, for sure, my hand is doing some positive work, and we can talk about that in a moment. But right now, I'm just focusing on the work that friction is doing. While the stylus goes out to you, friction does negative 26 joules of work. Now, then let's imagine I start bringing the stylus back in, just because I want to. And I start bringing the stylus back in eventually to the original spot that it started all this from. On the way back in now, the stylus is now coming back to me. So now it's going in the other direction. It's going in the negative direction now, right? Friction will naturally necessarily flip its direction. Because friction's always opposing the velocity of an object. So now friction's pointing toward you. Again, not a surprise. I'm not trying to say anything tricky. I'm just trying to break down something and explain it. So now when the stylus is coming back to me, the displacement direction has flipped. The force direction has flipped. So now it's a positive times a negative. That's still a negative. So on the way back, even on the way back, the work being done by friction is again a negative number. If we go all the way back to where we started from, the full 2 meters, then it's again negative 26 joules of work being done by friction. And none of that's supposed to be a surprise. Again, remember, that's why on the way out, perhaps friction, it might be slowing down the object for all I know, robbing it of kinetic energy, or certainly making it slower than it otherwise would go. And then on the way back, same thing's happening. So friction on the way out removes kinetic energy, and on the way back also removes kinetic energy. On the way out, friction does. Yeah, now I'm glad John is adding to this. Let me be very careful. I mean, I think I agree with him, but let me, especially if you're looking at the chat, what he's saying, the numbers are equal. The number on the way out is equal to the number on the way in. But here's the big point that I'm making that I'm going to contrast with something else in a minute. I'm saying for that total round trip, friction did a lot of negative work. Friction did negative 26 joules on the way out, and then it again did negative 26 joules on the way in, right, for the entire round trip. And by the way, that's why, for example, if the stylus were rubbing against my hand the entire time, it would generate some heat on the way out. Let's even say it's my top hand. My top hand is going on, it's like the bottom end is like rubbing against it, slowing it down, exerting friction, doing work. And you could tell that my top hand is losing kinetic energy because it's like generating heat. that's like that represents or indicates the energy loss from the system. Heat's dissipating into the environment, so it's getting hot. And then when my hand comes back the other way, it continues to generate heat. Like it's an energy loss, a mechanical energy loss from the system in both directions. So for the total round trip, I'm saying friction does a net amount of work that's in magnitude very large. And if it's a case of friction, it happens to be negative. The key point being, it's not zero. It's like something. Now, I think that agrees with what John's saying, but I'm just making sure. And I'm going to argue one further point. If you don't like to think about friction because it's confusing, because it's negative, you can just talk about whatever's pulling the stylus out. Say some string. We're pulling the stylus out toward you while the string is pulling it toward you. It's pulling forward and the stylus is going forward, like they're both positive. So the string or my hand or whatever that's pulling this stylus would be doing positive work toward you. But then on the way back, the stylus is coming back. The stylus is now being displaced negatively, and the force now would be in the other direction. The force would also be negative. So on the way back, it would be a negative times a negative. That's a positive. I'm saying on the way out, whatever's pulling the stylus is doing like positive 26 joules of work. And then on the way back, it's doing another positive 26 joules of work. That's a net amount of 52 joules of positive work for the whole round trip. So I'm saying, and both of those cases, whether you're talking about the tension that's pulling the stylus or you're talking about the friction that's opposing the stylus, either way, what I'm saying is those forces are what I would call non-conservative, because over the round trip, they do a net amount of work that's very much not zero. They don't, like one net removes energy from the system and the other one net adds energy to the system, but they don't, neither one of those conserves the energy. They're doing stuff around the round trip, like friction, tension, the normal force. They are non-conservative. Now contrast that, like, and again, hopefully all of what I'm saying, like, if you just look at it in the abstract, you're like, yeah, I knew that. Yeah, I knew that. Yeah, I knew that. Like, hopefully none of what I'm saying is like new information, but you might even just be thinking, yeah, duh. Like, I don't even see, like, why is that even like duh? Okay, duh. But now contrast that. I mean, and maybe you're not saying duh, but if you're wondering why I care, contrast that to an equally simple but subtly different force like gravity. Contrast it to gravity. Let's look at a round trip. And remember, my whole focus right now is what is happening during round trips, or what a physicist would call a closed path. In fact, let me pause for a second and be clear about those terms. They ultimately mean the same thing, but round, we're all in one dimension here. Everything I'm assuming is in like one axis of space. So when I say round trip or closed path, I mean like going out and then coming back. I don't literally mean doing something round, like that's like, I don't literally mean round. I mean there and back. I mean ending up wherever you started. That's what I mean by technically a closed path, or informally a round trip. Now let's look at a round trip or a closed path under the influence of gravity. Okay, if I throw this thing up, okay, that totally didn't work. But if I throw this, that didn't work again. But if I throw something up, if I throw a mass of m up to a height h, and then let it come back down to zero from whence it came, let's look at what happens there. On its way up, gravity is pulling down. Let's call up the positive direction. Let's call down the negative direction. On its way up, gravity is pulling down. So on the way, and the force is down negative mg. The thing is displacing up to positively to a height h. So while it's on its way up, the work being done on it is negative mgh, like negative force times a positive displacement yields a negative work. So on its way up, the work done by gravity, on its way out, up, the work done by gravity is negative mgh. That's negative work. Gravity is removing kinetic energy from the system. And yeah, of course, the system is getting slower and slower and slower until it reaches a peak height of h and an instantaneous speed of 0. But now, please note, all of this may sound so simple and so obvious, and maybe we're all tuning out, like, I don't know, but note what happens now. Now the object starts to come back down. It starts displacing negatively now, continuing its round trip, just like the other example. But here now, gravity doesn't flip direction. Gravity continues to point down. Gravity is always pointing down. Friction is always opposing our motion. Gravity is always pulling down. That's a different always. Gravity is pulling down while the thing goes down. So now the thing is displacing like negative h, and the force is still negative mgh. So now we have a negative times a negative. That's a positive. On the way down, gravity is doing positive work, mgh. So on the way up, gravity and of course, like the thing is speeding up now, it's gaining kinetic energy. So on the way up, gravity did negative work, negative mgh. And on the way back down, it did positive work, positive mgh. So unlike the friction case, because of this one subtle difference, that friction always opposes your motion, which means that friction actually flips its direction when you do a round trip, gravity doesn't flip its direction. It always just brings you down. So for a round trip under the influence of gravity, the total work done is 0. That's different from friction. Gravity, to get you from there to back, doesn't add or remove any energy from you for that round trip. Similarly, a spring is the same way. A spring, as you're bringing it, as you pull something out, displace it away from equilibrium, the spring is pulling toward equilibrium. The spring is doing negative work. Then when you release it and the spring starts bringing the object toward equilibrium, it's continuing to put, the spring always pulls toward equilibrium. So now when an object is coming toward equilibrium, it's being displaced in the same direction as the force. So on the way out, it's negative work. On the way in, it's positive work. Negative 1/2 kx squared, positive 1/2 kx squared. So the net work done by a spring and by gravity, the net work done over any round trip is 0. Both springs, the spring force, the elastic force, and the gravitational force from here on in, we're going to categorize as conservative because evidently they conserve energy. To get you from here to there and back, they won't do any work on you for a round trip. If you end up at the same place, you'll end up with the same energy. That unlike friction and normal and all. So let me just say, and I'm going to look in the chat. So I'm saying, I'm going to put it mathematically now. Oh, yeah, okay. So I'm saying in English, I'm saying any force that does 0 work around a closed path is known as conservative. And I'll denote conservative forces from now on F sub C. And I'm saying now, the way I can put this mathematically is any force that produces 0 work around a closed path, we're going to call a conservative force. So I'm introducing a new piece of mathematical notation here. I think most of you probably have not seen this mathematical notation. Even if you have heard a million times all the English I just said about physics, I now want to put it in mathematical terms and say, I mean, you look on this page, I'm saying there's a symbol which looks like an integral symbol that has a circle on it. That's a standard mathematical symbol that stands for what we call a closed integral. A closed integral is a definite integral. Remember, definite integrals in general, like the integral from A to B of blah, 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 blah. A definite integral means that you evaluate from one endpoint or one bounding value to another endpoint or bounding value or limiting value, whatever you want to call it. Definite integrals, you evaluate from A to B or from x1 to x2, or in our case, often from x equals 0 to x naught or something like that, right? What from now on, again, this is just like a thing of math that I'm saying, A definite integral is one that is evaluated from a boundary to another boundary. A definite integral does give you an actual numerical answer. It gets evaluated. This kind of integral is a definite integral. It does get evaluated and all that, but this kind of integral, instead of evaluating from like A to B, we evaluate from A to anywhere we want back to A. It's called a closed integral if both of its boundaries are one and the same. If we're integrating to somewhere and back, okay? Any force that produces an integral of 0 over this closed path, or any force for which the closed path integral is 0, is from now on what we're going to call a conservative force. And the two conservative forces that we know of so far in this class are gravity and elasticity. I mean, the gravitational force and the spring force. There will be more in this class, such as the electrostatic force. But those two are the conservative forces we have thus far. Okay, and stop me if I'm like, if you want. Now, what am I going to do with this? Like, what's so I'm okay. Oh, wait. Great question in the direct chat. Okay, this is a very good question in the direct chat. It's direct chat. I'm not going to read the name, but I am going to read the question. And it is even though so the question is this like the thing that I've written on the page here? Is this because when you integrate and input the ranges, they equal 0? Now, I know what this question, I think I understand what this question, the question sounds like it's saying, I mean, hold on, I'm sorry, 1 second, I'm sorry. Things happening. Wait, okay, so I'm looking in direct chat. Sorry, I'm just getting to. Right. Okay. No, this is it. Right. So I totally do get this question. It's really legitimate. And in fact, there's like now development in the direct chat question where it says like, the question says like the ranges are the same number. So 1 minus the other is 0. Okay. It's a really good question because it really shows that someone's paying attention to what I'm saying. But what I'm saying is super subtle. So my answer is actually no. Like, let me put it this way. I'm telling but I'm very glad I'm being asked this. I'm telling everybody that there's a thing called a closed path integral. That means you're integrating from one place to another. And maybe I should do an example of this in a second, but wherever you integrate from and where you integrate to is what you plug in for, the value of the independent variable when you evaluate. So here's what I'm saying. Like, yes, a closed path integral means you would integrate from like x equals 3 to x equals 3. Yes. But that means then you plug in the same value of x to the answer you get for the integral. Like you integrate in one direction and you plug in like values, then you integrate in the other direction and you plug in the values. And what I'm saying is this, yes, like when you evaluate an integral, you don't literally subtract one endpoint from the other. What you do is you plug in the endpoints into the functions that you got, and then you subtract one function from the other. Subtle distinction, but so what I'm saying is this. Closed path integral does mean that we're going to integrate from here to there and back. Yes, we're going to integrate from a place called like x equals 3 and go back to x equals 3. But we don't literally subtract 3 from 3. we would subtract the function with 3 being plugged in minus the function with 3 being plugged in. And what I'm ultimately saying is that in some case, right, but so what I'm saying is that, in fact, if you do this out, you will find that with some forces, even when you integrate from here to there and back, you won't get 0, because like in the case of friction, the minus signs that you'll be putting in, the minus signs will sort of be there in one direction and still be there in the other direction. So it will kind of end up being like 3 minus minus 3 in a way, like that's like almost an analogy. But I'm saying the way the minus signs will work with some forces, you'll end up subtracting a negative and you won't go back to 0. But with other forces, when you with other forces, when you do the whole integral, you will end up with 0. What I'm really trying to say, and it's a really good question, because again, this is a subtle point. I'm saying closed path integrals always mean integrate from here to there and back. Not all closed path integrals will yield 0. If they all did, they wouldn't really probably be that worth studying. The closed path integrals of some forces will not yield 0. We call those forces not conservative. Any closed path, any force for which the closed path integral does yield 0, we call a conservative force. That would be gravity and the spring force. It totally depends on the force. Yes. So the person just put in direct check. So it depends on the force. Yes, that is 100% what I'm saying. In fact, so this is like a funny mathematical expression here at the top of the page. When I say like closed path integral of fc dot dx triple equal sign 0, what I'm really trying to say there is I'm saying for any f for which the closed path integral equals 0, we will define from here on in that f to be FC. No, let me say this again. From here on in, the definition of an FC, the definition of a conservative force is a force such that its closed path integral yields 0. That is only true of some forces. And that is the distinguishing feature of some forces that we want to super care about. The forces that actually meet that mathematical requirement are going to be called conservative from now on. The only examples we have so far in this class are the spring force and the gravitational force. And lastly, what it says at the bottom of this page in like tiny red handwriting that you can't read, it says at the bottom, like equilibrium. That's what it says in the red at the bottom. Why did I write that? Because I'm saying mathematically, the property of gravity and elasticity that we're looking at here is that their closed path integral like yields 0. In English, what I'm saying, like what they have in common in English, if you notice, is that both gravity and the spring force seem to have an equilibrium orientation associated with them. Like friction always opposes your motion, but friction doesn't want you to move to any particular place. If you're moving to the north, friction pushes to the south. If you're then moving back to the south, friction's pushing to the north. Friction doesn't care where you end up. It's just opposing what you're doing. Right? I mean, that's like interesting, but there's no equilibrium associated with friction. It's not like the rough table wants objects to be on one side any more than it does on the other. Friction is non-conservative. Whereas gravity and spring, with all this mathematical fanciness that I'm saying about gravity and the spring, one thing that we could just like see about gravity and the spring is they both seem to like want objects to be in a certain place. Gravity wants things to be on the ground. Gravity is always pulling everything down toward the ground, whether things happen to be moving up or they happen to be moving down. Gravity is just yanking them down. Same thing with a spring. Whether you happen to be moving away from equilibrium or you're moving toward equilibrium, the spring is yanking you toward equilibrium. So forces that seem to be associated with some kind of equilibrium, that's their hallmark indicate. If you see there's some kind of equilibrium associated with a force, that's a strong indication or a strong hint, clue, that probably that force will do a net amount of zero work around a closed path. It will be a conservative force. Okay, I'm going to look in the, so that's my point. Now I'm going to look in the chat. Oh, wow. All right, great questions, John Ford, in the chat. Like, I'm totally going to agree with like this. Wow. In fact, it's funny. This is going to come to haunt us in a couple of homework. There's a big homework assignment coming up, very much related to this second thing that John Ford put in the chat. And when that homework comes up, don't think, oh, that's John's, and it's a hard homework actually, but don't think when it comes up like, oh, great, thanks, John, because of his question, we now have this homework. No, like, so what John's saying, yeah, that's really good, right? Like, and I'm not saying that, so I should read these out. So what John's saying is, yeah, well, you guys can read the chat, right? Like gravity and the spring can seem different because gravity always seems like it's pulling you down, whereas the spring seems to have this center that we can move around. But it's exactly as John's saying there, like what gravity is trying to pull us toward is the center of the earth. And if we were to make a tunnel, and we literally do have a homework about this coming up, if we were made a tunnel all the way through the earth and we were pulled toward the center of the earth, we would move toward the center of the earth, toward the center, and then we would get to the center of the earth and we'd already be moving. We'd be moving really fast. We would keep on going to the other side of the earth and we'd be pulled back again toward the earth. That's absolutely right. It turns out that gravity works even more like a spring than we might realize. They both are associated with a certain equilibrium. And I'm not saying they're identical. They're not identical, but they both are conservative forces. And the thing that John is saying there is great. And again, I'm a big believer in, I don't just like the conclusion he came to, this whole idea of physics. If we can articulate our confusion and then articulate the resolution, then we're really doing physics, right? If you can identify what the issue is and then because otherwise you can't resolve the issue. If you, anyway, you get my point. It's a good point what John is saying, and it's true. Wait, multiple, well, if multiple gravities worked on one object at the same time, as long as all of them were conservative, the whole thing would be conservative. But I'm not quite sure what that means. Multiple gravities. What do you? Multiple gravities. But I can definitely say, if, and this is what I am going to say, the nature of a conservative. Oh, okay, totally. All right, everything John Ford is, and I'm assuming people can see the chat. I hope they can. But everything John Ford is asking in the chat now, like we actually have like a whole subtopic and set of homeworks on coming up. So I'm partly going to postpone. So they're totally on point questions. I'm kind of going to postpone my answer for right now, but I will say this: the nature of a conservative force is a great many conservative forces can act on an object all at once. And as long as they're all conservative forces, then the system will remain conservative. Like that is true. No matter how many forces are acting on you, as long as they're all conservative, then the total amount of work done will be zero. And we will see that pan out. So these are great questions. I'm going to go on. Okay, now I'm going to say, yeah, so totally. Okay, why am I talking about all of this? Like, what does all of this have to do with anything? Yes, what I'm saying is that the spring force is a conservative force. The spring force is a conservative force, and we care about the spring force very much in this class now. And it's about to be important to recognize that it's a conservative force. And I'm about to tell us why. But yeah, conservative forces, great question, Maisha, are totally applicable to springs. Now, here's how we apply this concept of conservative forces to springs or to anything else. remember, so the top line is just a reminder of what we started the class with today, or what we said when Monday. Like, remember, the work we do from somewhere to somewhere else, the work we do on a system transfers kinetic energy to that system. If I do positive work on a system, I give it kinetic energy. But here's the thing. Since conservative force will do no work on something for a round trip, this gives us a very big sort of predictive and computational advantage. Here's what I mean. If I do work on some object, if I work against a conservative force like gravity, and I bring an object up, so I'm bringing an object up, I know gravity is doing negative mg work. Sorry, I know gravity is doing negative mgh work, negative mgh work, negative mgh. So in order for me to bring the object up, let's say at constant velocity, I must be doing positive mgh work. I'm doing work on the object to bring it up to a height h. I'm doing work on the mass m to bring it up to a height h. So I'm doing positive work, mgh, mgh, mgh to bring it, okay, bring up to a height h. I've done positive work, mgh, to fight that conservative force of gravity. Now, the object is here. I'm holding the object here. I did all this work on it. I gave it all this kinetic energy. Now it's sitting here with no, like, and then I stopped it, right? So I removed all that kinetic energy. So now the object is sitting here. I did all this work on it, but it's sitting here. So it's got no energy. It's got no kinetic energy anymore. I gave it all this kinetic energy, but it's got no kinetic energy. Wait, okay, hold on. I know things are happening in the chat. Let me just like spit this out and then I'll look in the chat in a minute. I did all this work on this object. So I gave all this kinetic energy to this object. Now the object is sitting here. It's just sitting here. So it has presumably no energy. But all this work was done against a conservative force. I know how much work the conservative force did on this object to get it up here. It did negative mgh. I know that if this object was ever released, and if it was allowed to go back to its original spot, if it's allowed to complete this round trip, I know for a fact that the total amount of work on the whole round trip is to be 0. That is, I know if it did if gravity did negative mgh on the object to get it here, then in order for the object to come back to here, gravity is going to have to do positive mgh. In other words, just by knowing how much work was done on the way out, I necessarily know how much work is going to be done on the way back, because I know the total has to be 0, as long as we're talking about a conservative force like gravity. So when the object is just sitting here with no energy at all, I could totally predict that if the object were to fall all the way down through that height h, fall back to the ground, I can predict with total accuracy and total confidence that the amount of work gravity will do on this object to bring it back down to rest will be mgh. I therefore know the total amount of energy this thing will gain falling back down is mgh. Like, I know that the amount of 1/2 mv squared that this thing will have when it hits the ground will be that full mgh. I know this in advance because I know we're talking about a conservative force. So I have this advantage that any amount of work that's done for throughout some path under a conservative force, if I just choose to view that path as the outward leg of some round trip, then I can totally predict what the end of that round trip will be. Therefore, I can say, if I just want to save myself the experiment, and I want to save myself computational steps, I can make a confident prediction and save a bunch of computational steps and just say, you know what, while this object is sitting here at height h, even though it has no kinetic energy at all, since I totally know how much energy it's going to gain when it falls back down to the ground, since I know that already because this is a conservative force, I can say that the object is storing this energy. I can say, and I'm saying this now for the first time in this class, I know you've heard this concept a million times before in other classes, but I'm now asserting when we have a conservative force, because conservative forces necessarily do 0 work around round trips, we can take any trip we want under a conservative force and view it as the first half. the outward half of a round trip and say that wherever you are, you're storing up energy for your return trip. We're storing energy, and we can call that storage of energy potential energy. And literally, what is the amount of potential energy? Like, there's not a formula to memorize. Don't memorize, oh, potential energy always equals mgh, or potential energy always equals 1/2 kx squared or something. What potential energy is simply the total amount of work that the conservative force will do to restore the object to equilibrium. So what it says on the bottom line here, the equation, what's written on the bottom of this page, it's saying the amount of work that a conservative force would do to bring an object from some arbitrary position, call it x naught, back to 0 equilibrium. That amount of work that it would do, we're going to call the gain in potential energy. Like so when this object is sitting up here, even though it doesn't, I gave it all this kinetic energy to get it there, it's going to get all this kinetic energy on the way back down, right while it's sitting there. If I want to save a bunch of steps, I can say it's storing up all that energy as potential. I can say it. I didn't discover this. I'm deciding this because it works. When you say an object, so like this object, if gravity is going to do mgh work on the object to bring it down back to the ground from a height of h, then I'm going to say, oh, it's storing potential energy mgh. Like, where did I get the mgh from? Because that's the work that gravity will do to bring it back down to the ground. Force mg, displacement h. So the work that gravity will do is mgh. So the potential energy it has right here is mgh. If this were a mass on a spring, the work that the spring would do to bring the mass back into equilibrium, we found on Monday, was 1/2 kx squared. So the amount of potential energy we say the mass is holding or storing when it's sitting here at position x would be 1/2 kx squared, right? The potential energy is just a storage of the energy that will be gained when the work is done to bring the object back to its equilibrium. Where's the object stored? I'm just looking at the, okay, we have 8 minutes. Where is this potential energy stored? Like, this all sounds very mystical. Like, is there a box is there a bank where the energy is being stored? Some people say the object is storing the energy. Other people will say the energy is being stored in planet Earth. If, for example, if we're talking about gravity, some people say it's being stored in the system, the Earth mass system. I say where the energy is being stored is in our minds. This is just an idea that we came up with. It's not a false idea. It's a perfectly great idea. But I'm saying when we say that object is storing its energy, we're simply saying that we saw how much energy it got, that it accumulated in order to get there, and we're predicting how much energy it's going to get back when it comes back. We're just envisioning this whole round trip and realizing that we can use our knowledge to shortcut a bunch of longer computations. So the energy, the potential energy, is being stored in our minds. So from here on in, I'm defining potential energy. The gain in potential energy of a system is the amount of work that the conservative force would do to restore that system to equilibrium. That's what I'm saying. And I do want, like, from now, like, I feel like I've just taught it. Like, from now, you're responsible for it. Don't memorize that PE equals 1/2 kx squared, or don't memorize that PE equals 1/2 or 1/2 mv squared, God forbid, or anything. PE is the total, delta PE, the gain in potential energy of a system, is the total amount of work that will be done on that system to restore it to equilibrium. And there's a couple of therefores that follow from this. We've got 7 minutes. I'm going to do the therefores and bring this back to the spring. Let me just look. I do know that somebody had something in the chat. Let me just look. Oh, one second. So let me go to the next page. So now, I'm going to therefore say, so now to bring this like full circle, when I said a few pages ago, we're defining this thing called total mechanical energy. From here on in, the total mechanical energy of a system at a certain position, at a certain place, at a certain point in space, the total mechanical energy of a system will be all of its kinetic plus all of its potential. Again, potential doesn't even apply as a concept if the forces doing work are not conservative. But the whole idea of potential is we're assuming that only conservative forces are doing work on an object. So whatever we're believing that whatever kinetic energy they're taking away from a system when the system is moving out, they're going to give back on the way back in. So whatever kinetic energy you're losing, you're storing up as potential. And whenever you're gaining back kinetic, you're converting over some of your stored up potential. So we're saying from now on, it's a trade-off. We're saying that the total amount of energy you have at any given spot is your kinetic plus your potential. And I'm asserting then that for any conservative system, so any, sorry, yeah, okay. Sorry, I'm just looking at. Yeah, no problem. Thank you, Lucy. So I'll pause for a second. I'm looking at time. Okay, so 4 minutes. Okay, but just let me know when. Oh, okay, great. Thank you. No problem. So what I'm saying now is, from here on in, any system on which only conservative forces are doing work, any system on which no non-conservative forces are doing work, in other words, the kind of system we're talking about in our homework. Like in our homework, we have a system on which the spring force is acting. Friction's not acting on it. I mean, friction's not doing any work on it. Tension is not doing any work on it. The normal force is not doing any work on it. Only the spring force is doing work on the system. And even, by the way, if we were in the lab, even if the system were vertical spring, so even if gravity were also doing work on it, we would still be, that's also a conservative force. So systems like that, where all the forces doing work are conservative, what we're saying from here on in is that for the total mechanical energy at any one spot must be the same as the total mechanical energy at any other spot. As the system moves from place to place, all it does is trade off kinetic and potential energy. Again, from now on, potential energy is just a prediction of how much work the conservative force will do on the system in order to restore it to equilibrium. So from now on, and I know we have like 1 minute what I'm saying, or 2 minutes what I'm saying, from now on is the total amount of KE plus PE at any one given spot must be equal to the total amount of KE plus PE at any other given spot for a conservative system. In the case of our spring here, in the case of question 5, the KE at any given spot is 1F mv squared. KE is also always 1F mv squared. The PE, the potential energy for our spring, is the work that would be done by the spring to restore it to equilibrium. So that's 1F kx squared. So for our situation here, the total amount of 1F kx squared plus 1F mv squared over here must equal the total amount of 1F kx squared plus 1F mv squared over there. Whatever here and there we choose. So how do we know how to choose? And this is the wrap up right here. I'm saying we choose, we're always comparing two spots. One spot is the spot we're solving for, and the other spot is the spot about which we have information. Specifically, the other spot is the spot for which we know an instantaneous speed. So we pick two spots, the spots that we're solving for and the spot where we know the instantaneous speed. The spot we're solving for in this case was the spot at which v equals 3. That's what we were solving for. So on the left-hand side, we were solving for the x at which v equals 3, and I compared it to a spot for which I knew the v to be 0. I just chose that because I like the number 0 because it's easy to work with. So I chose the spot x equals 0.15 because I knew v was 0 there. Some of you might have, tacitly or explicitly, you might have decided to compare our unknown spot to the equilibrium position, where you knew the speed was 3.87, totally fine, and not any worse or harder. But either way is fine. That's how we did it. That's great news.
Yep, awesome.
Yeah. So that's how I did it. So that's where I got. So this was a full explanation of where I got the 1f kx squared plus 1f mv squared statement in the first place in the homework. That all of this is where I got it from. From here on in, the takeaway, the GDP is, for any conservative system, the total amount of mechanical energy over here must equal the total amount of mechanical energy over there. I think, and I'm totally out of time. Okay, thank you for being so no new homework. Just keep on keeping on. I will start getting things back to you. Thank you so much for being so patient. We are done. You all rock. I will turn off the recording. Thank you all so much. Thank you. Great. Have a great everything. Have a great